Hi, welcome to Elementary Algebra. This series will discuss traditional topics usually covered in an elementary algebra course. In this first unit, we're going to talk about perhaps the most important question in the whole course, and that is, what is mathematics? It's important that we have a bit of a view as to what this subject is as we start, mostly so that we can kind of file it away in our brain in the right way. If we don't, if we view it as something that it's not, then it gets very difficult because we'll run into roadblocks in our thinking as we go down the road. Learning becomes much more difficult. So, the question is, what is mathematics? Think about that for a second or two. Some people think that mathematics is just a series of rules that you have to remember, and on occasions it feels a bit like that. There's thousands and thousands of rules that are just impossible to remember. Others think that it's just about knowing numbers, being able to count, being able to multiply and divide, or knowing how to solve problems. Well, there's no question that all of these things are part of math. But for right now, perhaps the easiest way to think about this subject is the way that Galileo spoke of it. Galileo said, "I mean the universe, it cannot be understood unless one first learns to comprehend the language in which it is written. And it is written in the language of mathematics." Galileo suggests that mathematics is a language used to describe the world around us. We clearly know that we use it often to describe how much something costs at a store or how much money we have in our bank account. But let's explore this in another way too. Let's consider what would happen if there were no numbers, and you were trying to talk to a friend about something as simple as, say, how tall a tree was. How would you do that if you didn't have numbers to describe it?
Well, shoot, Vern, how tall do you reckon that there tree is?
That tree there? Well, I reckon it's very tall.
Are you sure? I mean, that tree way up there, that one looks very tall. But that tree down below there, I think that's just pretty tall.
Well, very tall is bigger than pretty tall, so that tree up there has got to be very tall, not pretty tall.
Oh boy.
If there are no numbers, you can't say that the tree was 42 feet 6.5 inches tall. In mathematics, we use numbers and systems to describe things from how tall a tree is to the amount of thrust it takes to launch a space shuttle into orbit. These are not the only things that we describe. Let me give you an example of something that you're familiar with, something that you've probably used many times today. Now, you don't need to write this down, but there's a number system that you've used, as I said, many times already today. And it's not the regular counting numbers that we traditionally use. It doesn't count from 1 to 200 and keep going on. But it starts, and after a while, in counting up, you end up where you started, and start again. Can you think of what that might be? Well, I'm sure you've looked at a clock many times today, and it's based on a different number system than the real numbers. Let's think about the minute hand, say. If you think about it as a number system, it starts with 0, and it goes up to 59. After 59, the next number is 0. That's not what regular numbers do. It's a different number system, and mathematicians study things like this. It has a name. It's called modulo 60. And it has a couple of strange properties. For example, if you multiply 6 times 10, what would you get? Yeah, you would get 0. This also means that in modulo 60, 0 could be divided by 6 and not be 0. Now, we're not going to study modulo 60 in this course. We're not going to study any strange number systems. I think that you would find it interesting, but in this course, we'll be using just the regular numbers we're used to, the counting numbers, the fractions, the square roots, things of that nature. I hope you're going to find them easier than you did in the past if you think about them as a language and that everything we learn describes something out there in the world. Now, I'm telling you that this is a language, but it's always nice to have more than one person tell you that something is something. To that end, we're now going to hear from two professionals where mathematics plays a core part in their industry. The first is Jay White, who works with three-dimensional video capture, the process which is used in creating video games and many of the movies we see today. The second is Alan Adams, who was part of a team that developed a computer program which helps engineers create superstructures or skeletons of buildings quickly and cost-effectively.
Motion Capture 101. Every one of us has played a video game at one time or another. And the neat thing about video games is they take place in three-dimensional space. That means I have length, width, height, and I can travel along those space. And one of the key technologies mathematically of being able to create a game is motion capture. Motion capture is the ability to take a body and find it in 3D space and then translate that back to a director and says that's where that body is located. Then as I move along a road, or I move along a path, or I fly an airplane, or I drive a car along a path, and I know if someone is behind me in the game or someone is in front of me. Now mathematically, we have to understand how cameras work. Cameras are two-dimensional. Two-dimensional means it has one dimension up and down, one dimension side by side, but no dimension in depth. So if you had a single camera on me, you wouldn't be able to tell whether I was 2 feet from you or 20 feet from you.
Motion capture is accomplished by putting markers on the object you wish to capture and then recording the motion of each object. Sophisticated computer programs record the motion of each marker from each camera and then create a tracing of the markers. The more cameras you use, the better at the accuracy of the tracing. Wireframe models are then created, giving a better view of the motion. Programmers can then tie each marker to a piece of the actual artwork that will be used to represent the motion. Each location of each marker recorded at 1/100th of a second is tied to the piece of artwork, and that's what brings the artwork to life. Sometimes, as in capturing this intricate facial movements, many markers are used in a very small area, but as you can see, there's a great result.
Now we're in a process of directing or filming for a game or a simulation. We need to have 3D space, which means we have more than one camera. We may have one camera in front, one to the side, one overhead, or quite a few cameras. And when we have those quite a few cameras, instead of making it more complex, it actually makes it simpler. You have to think of a laser beam in the middle of each camera, and that laser beam is going to come out and hit a position on my chest. One from camera front, one from camera side. And if we use classic geometry, which is distance and angle, then we can find myself in 3D space with just 2 cameras. Now typically in motion capture we use more than 2 cameras. So now we're finding myself in multiple length, width, height angles to the center of my chest. Now your mathematics has to be very quick because each camera takes a snapshot maybe 16 times a second. So 16 times a second as I move around in my game simulation, I have to find my point on my chest in 3D space 16 times a second. So now we have to do some very quick math and we have to do some very complex math. So if we're finding one point from 3 positions, we're now solving 2 cameras can find me, the 3rd camera corrects it. So now you have 3 equations, actually 3 knowns, which is one of the simplest parts of finding yourself in 3D space.
Let's look at an example of this. The process begins with calibrating each camera to a specific point in space. For us, it's the red ball. Next, we place the object that we wish to capture with markers in all the appropriate spaces. We're going to focus, for our purposes, on just this one white marker. Each camera will identify the marker and calculate the location of the marker with respect to the red ball. For our purposes, this may mean that from the red ball we need to go up 20 centimeters and to the right 37 centimeters. Since each camera is finding the same spot on the object, when you look at where each of those cameras find that spot and you draw a line from the camera through that spot, we have a place where all of those lines cross. That would be the exact location of the white marker in three-dimensional space.